Welcome to Module 7. Today's module is studying the properties of liquids and solutions. Module 7 will be discussed in one video, which will cover the following topics: the energy associated with the phase transitions of matter, the general properties of liquids, solutions, and concentrations. The learning outcomes for Module 7 are: calculate the energy associated with phase transitions, identify the solubility of certain compounds, and solve questions relating to concentration. Remember from Module 2 the three states of matter: solid, liquid, and gas. The change from one phase to another is called phase transition. This transition either requires or produces energy. For example, heating a cube of ice will cause it to melt and change the state from solid to liquid. On the other hand, cooling water will cause it to freeze. To understand the concept of phase transition, let's cover some definitions first. Evaporation, or vaporization, is the escape of molecules from the liquid state to the gas or vapor state. With evaporation, we also need to understand vapor pressure. When a liquid vaporizes in a closed system, some of the molecules in the vapor or gaseous state strike the surface and return to the liquid state by the process of condensation. The rate of condensation increases until it is equal to the rate of vaporization to reach an equilibrium. The pressure exerted by a vapor in equilibrium with its liquid is known as the vapor pressure of the liquid. The vapor pressure of a liquid is a function of temperature. Boiling point. The boiling point of a liquid is related to its vapor pressure. Boiling point is the temperature at which the vapor pressure of a liquid is equal to the external pressure above the liquid. Freezing and melting points. As heat is removed from a liquid, the liquid becomes colder and colder until it reaches a temperature at which it begins to solidify. A liquid changing into a solid is said to be freezing. When a solid is heated continuously, a temperature is reached at which the solid begins to liquefy. A solid that is changing into a liquid is said to be melting. The temperature at which the solid phase of a substance is in equilibrium with its liquid phase is known as the freezing point or melting point. Different compounds require different energy to heat up. This concept is known as the specific heat of a substance, which is the quantity of heat lost or gained required to change the temperature of 1 gram of that substance by 1 degree Celsius. From the definition, we can see that the specific heat can be calculated by the following formula. Specific heat is equal to heat over mass multiplied by delta T, where delta T is the change in temperature. If we rearrange the equation, we can then calculate the heat required to change the temperature of a certain substance. Heat equals mass multiplied by specific heat multiplied by delta T. For example, the specific heat of liquid water is 4.184 joules per gram Celsius. So, we need that much of heat to increase the temperature of 1 gram of water 1 degree Celsius. The energy required to change exactly 1 gram of a solid at its melting point into a liquid is called the heat of fusion. The heat of vaporization is the energy required to change exactly 1 gram of liquid to vapor at its normal boiling point. To study phase transition, we will investigate the example of water. This graph helps us to understand the energy required to evaporate a sample of ice. The y-axis represents temperature, and the x-axis represents the heat provided to the sample. If we have a sample of ice at minus 20 degrees Celsius, When we apply heat, the sample absorbs that heat and starts to warm up. No ice will melt yet, as the temperature is still less than 0 degrees Celsius. When we get to 0 degrees, the ice starts to melt and change from solid state to liquid state. The temperature remains 0 for some time while the ice is melting. So we say the sample absorbs the energy in melting and not increase its temperature. After all the ice has melted and changed into liquid, then the water starts to warm up from 0 degrees. For every 1 gram of water, we need 4.184 joules to warm it 1 degree Celsius, and this is the specific heat. When the water reaches 100 degrees Celsius, we start to see the water boiling. Once we get to that stage, you notice that the temperature is not increasing anymore for some time. At this temperature, the water changes state from liquid to gas. After all the water has evaporated, the temperature starts to rise again. And now all the sample is in the gaseous state. Let's look at an example. How many joules of energy are needed to change 10 grams of ice at 0 degrees Celsius to water at 20 degrees Celsius? In this example, we start from ice and we need to warm the water up to 20 degrees Celsius. As we are starting from ice, then we have 2 stages in this question. The first stage is to melt the ice. After we melt the ice, then we start the second stage, which is warming up the water. For the first stage, we need the heat of fusion for ice, which is 335 joules per gram. You don't need to remember this number, and it will be given to you in the exam if needed. As we have 10 grams of the ice, we multiply 10 by 335 to get 3,350 joules. This is the energy required to melt the ice. Remember, at this stage, the temperature of the sample is still 0 degrees. The second stage is to warm up the water. We need the specific heat for water for this stage, which is 4.184 joules over grams degrees Celsius. To calculate the energy, we need to use a formula that we learnt previously. As we have 10 grams, we need to warm it up from 0 to 20 degrees Celsius, making the delta T 20 degrees. So, we need 836.8 joules. The total heat needed to do both these stages is the sum of both heats, which is equal to 4.19 times 10 to the 3 joules. Let's see another example. How many kilojoules of energy are needed to change 20 grams of water at 20 degrees Celsius to steam at 100 degrees Celsius? Again, in this question, we have 2 stages. The first stage is to warm the water from 20 to 100 degrees Celsius. The second stage is to boil the water and change the state from liquid to steam. The first stage, we need the specific heat for water. We have 20 grams of water at 20 degrees Celsius, and we need to warm the sample to 100 degrees Celsius. So we need 6.7 times 10 to the 3 joules of energy to do the first step. The second stage is to boil the water into steam. So we will need the heat of vaporization, which is 2,259 joules per gram. As we have a 20 gram sample, then we need 45.2 times 10 to the 3 joules of energy to turn all the liquid water into steam. The total energy to do both stages is equal to 51.9 times 10 to the 3 joules. However, the question is asking to calculate in kilojoules, so the answer will be 51.9 kilojoules. Remember, from Module 5 we covered the concept of solubility. let's revise some of the important definitions. A solution is the term used in chemistry to describe a system in which one or more substances are homogeneously mixed or dissolved in another substance. The solute is the component that is dissolved or is the least abundant component in the solution. The solvent is the dissolving agent or the most abundant component in the solution. Solubility describes the amount of one substance, the solute, that will dissolve in a specified amount of another substance, the solvent, under stated conditions. For example, 36 grams of sodium chloride will dissolve in 100 grams of water at 20 degrees Celsius. Some ionic compounds dissolve in water and some don't. It is related to the forces of attraction between the cations and anions. Sometimes the forces are so strong that water cannot form the hydrate ions and dissolve the compound. As there is no way to predict this information, you need to learn the following table that provides some examples of soluble and insoluble salts. Any ionic compound that contains sodium, potassium, and ammonium will always be soluble, no matter what the anion is bonded to. Likewise, any compound that contains nitrate will always be soluble, no matter what cation it is bonded to. Halogens such as chloride, bromide, and iodide are mostly soluble, except when they bind to three metals: silver, mercury, and lead. Sulfates are also mostly soluble, except when bound to three cations: barium, strontium, and lead. The important compound of those is barium sulfate, which is used in X-ray examinations. Remember from Module 5 we used the term like dissolves like. So polar compounds dissolve in polar solvents, and so on. For example, sodium chloride dissolves readily in water. Also remember from Module 5 we discussed the several factors that affect solubility. We will only revise temperature and pressure. The solubility of solids increases with temperature. For example, we can dissolve approximately 36 grams of sodium chloride at 0 degrees Celsius. However, we can dissolve almost 40 grams when we heat the water to 100 degrees. The temperature has a negative effect on the solubility of gases. For example, soft drinks contain dissolved carbon dioxide gas. When you get a cold soft drink from the fridge and drink it, the temperature of the drink rises to 37 degrees. This will reduce the carbon dioxide solubility, and it gets released in your stomach and you burp. Small changes in pressure have little effect on the solubility of solids and liquids. The solubility of a gas in a liquid is directly proportional to the pressure of that gas above the solution. The amount of a gas dissolved in solution will increase when the pressure of that gas over the solution increases. There are three types of solutions: saturated, unsaturated, and supersaturated solutions. A saturated solution contains dissolved solute in equilibrium with undissolved solute. An unsaturated solution contains less solute per unit of volume than does its corresponding saturated solution. In some circumstances, solutions can be prepared that contain more solute than needed for a saturated solution at a particular temperature. These solutions are said to be supersaturated. For example, if we add 39 grams of sodium chloride to 100 ml of water at 20 degrees, we can only dissolve 36 grams. However, if we heat the solution to 100 degrees, we can dissolve the remaining 3 grams of sodium chloride. Once we cool the solution back to 20 degrees, that's called a supersaturated solution. It has dissolved more solute than it can normally. Those solutions are not very stable, and if you add any more solute to them, they start to form crystals. The concentration of a solution expresses the amount of solute dissolved in a given quantity of solvent or solution. There are many ways to express concentrations. We will investigate 5 formulas at this stage. Mass percent is equal to mass of solute over mass of solution multiplied by 100%. Mass over volume percent is equal to the mass in grams of the solute over the volume in milliliters of solution. The volume percent is equal to the volume in milliliters of solute over the volume in milliliters of solution multiplied by 100%. Molarity is equal to moles of solute over the volume in liters of solution. And molality is equal to the moles of solute over the mass in kilograms of solvent. Let's cover some examples to practice these concentrations. What is the mass percent of sodium hydroxide in a solution that is made by dissolving 8 grams of sodium hydroxide in 50 grams of water? The question is asking to calculate the mass percent. So we use the formula mass percent is equal to mass of solute over mass of solution times 100%. Before we start, let's identify each component of the solution. The solute is sodium hydroxide, and we have 8 grams of it. The solvent is water, and we have 50 grams of this. The solution is the total of the solute and solvent, so that should add up to 58 grams. Now let's apply the numbers in the formula, and the answer is 13.8%. Let's look at another example. What masses of potassium hydroxide and water are needed to make 250 grams of a 5% solution? The question is asking to determine masses and provides 5%, so we would expect that this is the mass percent. Now let's identify each part. The solute is potassium hydroxide, and we have to calculate how many grams are needed. The solvent is water, and we have to calculate how many grams of this are needed as well. Solution is equal to the mass of the solute plus the mass of the solvent, which is equal to 250 grams. The mass percent is equal to 5%, or 0.05. Let's fill in the numbers and rearrange the equation to calculate the mass of the KOH. Therefore, the answer is 12.5 grams. The mass of water, the solvent, is 250 grams minus 12.5 grams, which is equal to 238 grams. Another example. What is the molarity of a solution made by dissolving 2 grams of potassium chlorate, KClO3, in enough water to make 150 ml of this solution? Remember, the formula to calculate the molarity is molarity equals moles over volume in litres. Let's identify each part. The solvent is the water. The solute is potassium chlorate, and we have 2 grams of it. According to the molarity formula, we need number of moles, not mass. Therefore, we divide by the molar mass of the compound, which can be calculated from the periodic table. The molar mass of potassium chlorate is 122.6 grams per mole. So, there are 0.0163 moles. The solution volume is 150 mils. However, we need to convert the volume to litres. To do that, we simply divide by 1,000, so the volume is 0.15 litres. Now we have all the required information. We can calculate the molarity, and it is 0.109 molar. This is the end of Module 7. Please practice the weekly exercises in your textbook and the questions you find in your workbook. We will meet face to face in the tutorial session, and this will be your opportunity to ask any questions or seek further clarification.